today I'm going to go over the chapter 11 comprehension check. Before we start number 8, I need to introduce you to the pH scale. You've probably heard of the pH scale, or you may be even really familiar with the pH scale. If you have a pool or a hot tub or something like that and you frequently test the water, you're probably familiar with these little strips that you put in the water to test the pH of your pool water. Well, the pH scale ranges from 0 to 14. And on the pH scale, it means we write it little p, capital H, and it stands for potential for hydrogen. And you're aware now that when we're dealing with acids and bases, we're talking about donating a hydrogen or accepting a hydrogen. And so the pH scale just measures like it's a compound's ability or its potential to either donate or to accept a hydrogen. And so down here at the very end, we have, so from 1 to 6, we have our acids, and from 8 to 14, we have our bases. And if you're 7, you're right in the middle, we call you neutral. And so these are the ones that donate hydrogens. These are the ones that accept hydrogens. For question number 8, it gives us 5 pHs. It gives us 1, 3, 7, 9, and a 14. And then it gives us, I hope it didn't mess you up, I rewrote them because I originally only had the 4 and I realized I left out some of the scenarios. And so for these scenarios, we have, we're gonna look for what is the most acidic. And so we've said acids range from 1 to 6, but the lower the number, the more acidic they are. So that would be number 1. Then the next part B is neutral. Just like we talked about, 7 is neutral. It's right in the middle, neither an acid nor a base. Which one of these numbers would be the most basic? So I'm looking for the highest step number because bases are on the 8 to 14 range. And so 14 is actually one of my choices. Then it just says which one would be more likely to be a solution of baking soda. There is actually a drawing of the pH scale on this page of the textbook. And if you look at it, you see that baking soda has a pH scale of 9. So you're just looking at the chart on that. And then number E says they turn anthocyanins pink. And so what is an anthocyanin? An anthocyanin is a compound that changes color based on its pH. And the number one example of these that you're gonna see in lab is red cabbage juice. You can actually take a red or a purple cabbage and you can boil it and you should get like a red or purplish colored juice. But when you change the pH of that liquid, the color changes. It's called an anthocyanin. And these are actually common sometimes in nature in different types of plants. Some plants, their colors will change based on the pH of their soil. And so when anthocyanins turn more on the pinkish kern, they are actually acids. And so the one that would be more an acid. Now, this question is assuming you've done an experiment where you take cabbage juice and you mix it with vinegar. And so if you did that, you would notice that it should turn pink. And so the pH of that vinegar that they tell you was 3. And so it would turn it pink. The pink is why I wrote acids as red, because I know a lot of those indicators, they'll turn acids in the red to pinkish range, just like it makes litmus paper red. And I also did bases as blue for the same reason. So question D, ask which one of these pHs is more likely to be distilled water. Distilled water is just water with none of its ions in it, just pure water. And water is neutral, so it's gonna have a pH of 7. So for comprehension question number 9, we are getting into some stoichiometry. I know you thought maybe we could make it through this chapter without it, but it's gonna be here for the rest of the year. So the question tells you, it says a student needs to neutralize 750 milliliters of a 5 molar solution of KOH. And then it wants to know how many milliliters of an acid solution would needed, it says, to get the job done. So basically I have a basic solution of potassium hydroxide and I'm adding an acid to it to neutralize it, and it wants to know how much acid I'm gonna have to add to neutralize it. And so first thing I'm gonna do for this problem is I am going to write the acid-base reaction. I'm starting with hydrosulfuric acid and I'm reacting it with potassium hydroxide. And so my products are gonna be water and a salt. And so, because the hydroxide and these hydrogens go to make water, and the reactants that are left over to make the salt is potassium and sulfate. And I'm going to put potassium first because it's the cation, and sulfate last. I got to check to make sure that this formula is balanced out. So the charge on potassium is a 1+, and the charge on sulfate is a 2-. And if you don't remember your polyatomic ions, flip back, or maybe you still have it written on your card. But I want to check that charge, so I'm going to do the crisscross method. So I end up with K2SO4. Now, once I've written the equation, I'm not done yet because it's not balanced. So I'm going to go through here and balance it. If you'll remember, when you balance this equation, I would recommend saving the water part and balancing it last. So let's go ahead and look at something that we have like potassium. I'm hearing my dog. So we have 2 potassiums here. We only have 1 here. So let's add a 2 here. And so now I know I have 2 potassiums. And let's look at sulfates. I can keep sulfate together since it's a product and a reactant. And so I have 1 sulfate and 1 sulfate. So let's start to look at hydrogens and oxygens. So in this one, I have 2 hydrogens and 2 hydrogens. So I have a total of 4 hydrogens. And for oxygens here, I have 4 oxygens plus 2. So I have a total of 6. On this side, I have 2 hydrogens and 5 oxygens. So I can see that this side needs double the amount of hydrogen, so I'm going to put a 2 here. What happens is that gives me a 4, and that makes my oxygens also be a 6. So I have 2 plus 4 is 6. So now it's all balanced out. So the question gives me some information about the potassium hydroxide. It tells me I have 750 milliliters of a 5 molar solution. They also then come on to give you a little bit of information about your sulfuric acid. They tell you you have 3.41 molars and you're looking for milliliters. So what I tell my students is on this, if you have no idea what to do, first thing I would do is I would calculate moles. Well, what do I calculate moles of? Well, I know all my information of potassium hydroxide, and I'm going to be taking potassium hydroxide and I'm going to be neutralizing it with the sulfuric acid. And I'm wanting to know how much sulfuric acid I have to add to neutralize the reaction. Well, the first thing I would calculate is how many moles of potassium hydroxide we have. This is a great place for you to pause it, to go and check your work from, this is like 2 chapters ago, to see if you remember how to calculate moles from molarity, and come back and see how you did. But we're going to calculate moles of potassium hydroxide. Hopefully you got similar to what I did. So I took 750 milliliters and I put it into liters because molarity is moles over liters. And I multiplied it by the molarity, because if molarity is moles over liters, and I get liters on the bottom, I can cancel this out and I'm left with my unit in moles. So when you do that, you get 3.75 moles of potassium hydroxide. Now you're going to take your stoichiometry knowledge and calculate how many moles of sulfuric acid we need to add to that to balance it out or to neutralize it. So I see that they react in a 2-to-1 ratio. I'm just going to keep it going right now. So I'm going to put moles of KOH on the bottom. And H2SO4 on the top. That way the KOH cancels out. And these numbers come from the coefficient. So I put a 2 on the KOH and a 1. And so that will give me my moles of H2SO4. And you should get, I'm running out of space, 1.88 moles of H2SO4. So I know that if I can add 1.88 moles of H2SO4 to my 3.7 moles of KOH, they will neutralize. Now, the next part of the question is, how can I measure out moles of H2SO4? You can very easily go from moles to grams, but the question is not asking for grams, it is asking for milliliters. So to go from moles to milliliters, you're gonna have to use this molarity information that they give you. So I've got 1.8. And I'm gonna switch the molarity because I want moles to cancel out and be on the bottom, and I want the liters to be on the top, which is why I inverted it. And I'm left with an answer in liters. You get 0.551 liters. There's still one more step, and that's that it asks you to put it in milliliters, and so we can very easily turn that into 551 milliliters. So let's recap that really long question, all right? They gave you information of the base, and they wanted to know how much acid you had to neutralize it. In order to do that, I needed to know how many moles of the base I had. So I used the molarity and the volume to calculate the moles. I then went from moles of KOH using stoichiometry to moles of the acid. I then used my molarity again to go from moles of the acid to volume. For question number 10, you should be doing a lab similar to this in class, and it gets very confusing, but this is a titration equation. And so what you're doing for this is we have an unknown concentration of our acid, and we want to know some information about it. So what you do in a titration reaction is then we're going to react our base with it and a known amount of base with it so that we can then calculate or determine the concentration of the acid. So for question number 10, I'm not going to write the whole question out because it's an extremely long question. But the first thing I would say is let's start with writing the balanced equation because that will help you understand what's going on better. I'm going to read it to you and then I'm going to write the equation. So it says a solution of H3PO4, so that's our acid, and it has an unknown concentration. So we don't know, like if it's 5 molar, 6 molars, we don't know any of that information about it. But we do know that we have 115 milliliters of this. And it's going to be titrated against 1.12 molarity of lithium hydroxide. So we have an acid, we know how much we have, but we do not know like the concentration or how many moles. And we're going to react it with a known amount of a base. And so then it's asking us how much of the base do we have to add to hit end point. And so the end point of a titration is the point where the equation is neutral or balanced. So you're going to have in your beaker a chemical that changes colors when the pH changes. And so you're going to be standing there drop by drop, adding your base to your acid or your acid to your base, sorry about that, and waiting on a color change. And when the color changes, you stop and you figure out exactly how much of that chemical you added. So we're going to start with writing the equation because that's going to help so much. All right, so this is basically what this equation is. We have our acid that we know some information about, but not all of it. Then we have our base, and we know it's a base. It has our hydroxide ion in it, and I know a lot of information about that. And it's producing my water and my salt. How did I get lithium phosphate? It's easy to figure out how to make the water. But to get lithium is a group 1A metal, so it has a charge of a +1. And phosphate is a polyatomic ion that you may know, and it has a valence of 3 negative. So we crisscross the charges so that we get a balanced formula. So now let's balance the entire chemical reaction. And if I look at this, I'm going to leave the waters, hydrogens, oxygens, all that for last. So let's look first at the metal. Let's do the lithium. 1 lithium, 3 lithiums. So I need a 3 there so that I have 3 on each side. The next, let's look at phosphate because it's a polyatomic ion in the reactants. And in the products, I'm going to keep it as 1. So we have 1 phosphate and 1 phosphate. So the only thing we're left with is really these hydrogens and the oxygens. So let's calculate out 3 hydrogens plus these 3, so I have 6. 4 oxygens plus 3, so I have 7. So over here for hydrogens, just 2. And for oxygens, we have 4, we have 5. So I actually need 6 hydrogens. So I'm going to multiply this by 3. That gives that 6. And then that gives me 4 plus 3. So that makes me have 7 oxygens. Let's take what they give us in the book and put it above the equation. So they tell us we have an unknown concentration of this. That's actually what I'm looking for, or in molarity of that. And then it tells me I used 115 milliliters of it. And it's reacting with a 1.12 molarity of lithium hydroxide. And it actually tells me exactly how much lithium hydroxide we use. It is 97.1 milliliters. So I know how much of the base, so I can actually calculate, just like we did in the past problem, how much of the acid. So the first thing we're going to do is we're going to go to moles. So you're going to calculate, I cannot calculate moles of the acid, that's what I'm looking for, but I can calculate moles of the base. So use the molarity, stop, check yourself, try to calculate the moles without me, and then come back. So I'm going to take the molarity that they gave me, 1.12, and I actually just wrote it as moles over liters because that's what molarity is. And I want to cancel out the liters on the bottom, so I'm going to multiply it by the volume. Now they gave me volume in milliliters, but I can easily convert that to liters. So liters cancels out, and I'm left with 0.109 moles of lithium hydroxide. Now, if you'll remember, our goal is to figure out what they're asking, the concentration of the acid. So before I can do the concentration, which is molarity, I need to know the moles of the acid. So that's really what I'm trying to calculate. All right. So I'm trying to figure out this much moles. Now, using stoichiometry, I can go from moles of the base to moles of the acid. And so they react in a 3-to-1 ratio. I'm just going to take this and I'm going to multiply it by 1 mole of the acid of H3PO4, and I'm going to put it over 3 moles of the LiOH. And these come from my balanced chemical equation. My lithium hydroxide cancel out, and I am going to put in my calculator 0.109 divided by 3. And you should get 0.0363 moles of your H3PO4. Now the final part of the problem is it's asking you for the concentration of the H3PO4. Concentration, I need moles and I need liters. And I have my moles all the way down here, and they gave me my liters. So you can actually now go back and you can calculate your concentration of the acid that you're going to use. Make sure that you put your volume in liters, and you should end up with 0.316 molarity of H3PO4. Quick, just recap in case you got lost in all the steps. We're doing a titration reaction. We have an acid, we know how much of the acid, but we don't know the strength or the concentration of this acid. We're reacting it with a base, and we actually know all the information about the base. I know the molarity of the base, and I know the volume of the base. Well, with molarity and volume, I can calculate moles. So I'm going to go from moles of the base to moles of the acid using the balanced chemical equation. Then when I know moles of the acid and I know volume of the acid, I am able to calculate the concentration of the acid. Comprehension check number 11. I actually do not like the way that they teach these chapters, these problems in the book. So these are solution dilution problems. You have a solution and it's going to be concentrated, and you're going to be adding water to it to dilute down the solution. And the book gives very complicated examples in a way of explaining this, when there is actually a really simple dilution equation that you can use. And so I'm not going to go so in depth to this, but there are there are many more YouTube videos of people teaching you the dilution equation. But really simple, this equation is M1V1 is M2V2. So this is the dilution equation that's not mentioned in the book that I actually really like. So in this equation, remember, M is not going to stand for mass. It actually is molarity. It's a capital M. And V is for volume. And so M1V1 is going to be your solution in your first situation. It kind of reminds me of the combined gas law, where you have, in the gas laws, you have a vessel of a gas in one situation and you just change its situation. It's kind of the same for this. We have a solution, we have its molarity and its volume. And if we want to calculate it by diluting it down, we're going to use this equation. And I'm going to just give you an example, do this problem with this equation, and hopefully that will help you see how to use it. The question tells you that you have a solution of a 9.12 molarity, and it's magnesium chloride. And we're going to be doing an experiment, but we need 500 milliliters of this, and we need a 4.5 molar solution. So how can I make that solution from what I already have? So basically, I've got in my cabinet one solution of MgCl2, and it's not exactly what I need, and so I want to alter it a bit. And so the first solution, the first scenario, it tells me it's a 9.12 molarity. Well, we'll leave those off. And I don't know how much of it I need. I don't know the volume. But it tells me I want to make a solution that has a molarity of 4.5, and I want 500 milliliters of that. So I now would just take this and I am going to solve it for V. And so if I multiply these together, I get 2,250 equals 9.12 V divide and my volume equals 246 milliliters. Now my answer is still in milliliters, and the reason why it is because I left this in milliliters. I could have put it in liters and my answer would have been in liters. But if you use M1V1, M2V2 for dilutions, basically you just have the molarity and the volume of the first solution, and it's equal to the molarity times the volume of the second solution. And it's a little bit easier way to calculate it.